Okay, this is a brief tutorial on ionic bonding and covalent bonding. The few things you're going to need are this handout, which will be included with this tutorial. So this will be on a half sheet of paper, and you'll need your periodic table. You're going to need your polyatomic ion list and your shapes list. These two things should be on the back of your periodic table. Should be pasted on the back. Alright. So first of all, your cations are going to come from mainly two places. It's going to come from here and here. Or it could be ammonium. This is the only polyatomic that's a cation, NH4 plus 1. Otherwise, your cations are going to come from here for the most part. Column 1 or column 2. Column 3, usually you'll see that in covalent compounds. Sometimes you'll see aluminum, like aluminum oxide or something like that. So you may get column 3. It's possible. But usually it's 1 or 2, sometimes 3. Okay, your anions, on the other hand, are going to come from here. You're going to get a 3 minus, a 2 minus, and a 1 minus. So you're going to see those come from 5, 6, and 7A. Or, very commonly, you'll see an anion come from this list, the polyatomic ion list. Okay, so when we fill these in, where it's asking for ions, when you fill these in, that's where they're coming from. You're gonna get the charges from here, or from here, or from memory. From this, we'll put a couple more stars on here to show that it's important to know the symbols and names and charges that they make. Okay, so that's covers some of the background of how to do this, where the charge is coming from. Now we'll go right into it. So barium chloride, we'll just look at a couple of these. 1, 2, and I'm thinking number 8. So barium chloride, barium, where does that come from? This is asking for the cation. So again, the cations here and here, and sometimes here. Okay, barium, it's right here, second column, so it makes it 2 plus. So we write Ba2 plus. So a common mistake students make is sometimes they'll write just Ba without the charge. So you're just showing the atom. This is asking for the ion. So you write 2 plus. And chloride comes from, so your anions are going to come from here or here. So this is chloride. So this is just talking about the monatomic or single atom ion. It's in column 7. Column 7 makes a -1. So we're going to write Cl -1. Then when you write the compound, you crisscross the charges. That 1 goes here, and the 2 goes here. So it's going to be BaCl2. In other words, why are there 2 chlorides? Because this is a 2 plus, and you need 2 of these to balance the 2 plus. Okay, so that's what you're doing when you crisscross, is you're balancing the charge. Okay, this one's a little bit different, so we'll take a look at this one, and then finally we'll take a look at this one. So magnesium phosphate. Here's our cation, magnesium, second column, 2 plus. So we write Mg2 plus, phosphate. So be careful, because phosphate, this is asking for phosphate. Okay, this right here is not phosphate, that's phosphide. Okay, so remember, all the monatomics, they end with "ide". So phosphide is that, phosphate is that. Okay, so phosphate, that's what I write, PO4 3 minus. So I write PO4 3 minus. I'm ready to crisscross. So keep your parentheses around the polyatomic, everything but the charge. And it's saying I need 3 mgs and 2 PO4s when I crisscross. Alright, so I write mg3, keep it in parentheses, PO4, 2. Okay, I'll show some scratch work here. mg, it says I need 3 of those. 1, 2, 3. So that's a total of 6 plus on the cation side. For anions, it's saying the formula you just wrote says 2 phosphates. Here's 1, here's 2. And that's a total of 6 minus. So again, that's what you're doing when you crisscross charges, is you're getting the smallest ratio it takes in order to balance these two charges. Okay, so we'll look at one more ionic bond, and that's one with a transition metal, because the way you name them is a little bit different. Everything else is the same, but the way you name them is going to be a little bit different. So the compound, same thing. The charge is 1, so there's 1 cobalt and 2 bromines, or bromides, sorry. So you write BrCO, Br2. But when you go to name it, it's a transition metal. So all the transition metals are here. Okay. In fact, sometimes bismuth and lead, tin is in there. Okay. A couple of these, but for us, I will try not to use these. So just worry about transition metals here, the D block, in other words, cobalt here. So when I go to name it, I'm going to need a Roman numeral 2 to show what charge it makes. Because transition metals, cobalt could actually be this or this. So transition metals, they kind of have their own rules. They don't really follow these octet rules, which is how these come about, these charges come about. Okay. So these are pretty standard. It's always +1, always +2. Not so on these. They could be +1, +2. They could go like tungsten, could be like a +6. So you have to specify by writing it in Roman numerals what charge it makes when you go to name it. So we call cobalt to bromide. Okay, and always change the ending if it's monatomic. In other words, if your anion comes from here, change the ending to I. Okay. So that concludes our ionic bonding. And now we'll take a look at some covalent. We're going to clean off our periodic table because we're going to show some Lewis dots. Because covalent is sharing electrons. Right. And ionic was full-on charges. Okay, full-on giving and taking of electrons. So you're going to need this and your periodic table to do this. And you might need the dot structures. Okay. Carbon's 4 dots. Column 5, you have 3 single dots. Column 6, you have 2 lone pairs and 2 single dots. And then column 7, the halogens, 3 lone pairs, 1 single dot. Okay. We'll take a look at a couple of these. Number 2 and number 3. Alright, central atom is the one with the most single dots, and it's usually written first, so that would be carbon. So here's carbon. Carbon's here. What column is it in? It's in 4A. So now here's where this comes into play. We look at 4A, and then we look and see what shape it makes. It makes a tetrahedral. So when you go to draw it, you're drawing. So when you go to draw it, your drawing should look like that. Okay, so it's in 4A, name of shape, it's a tetrahedral, and when you go to draw it, you should write C, and it's not going to matter where you put the H's. So I'm kind of following this scheme here. It doesn't matter where you put the H's or the F. or the F's. So I'll just put them like that. Okay, and we used up single dots on carbon. It has 4 single dots, and we use them to make these dashes. And now here's where we add dipoles. So the En of fluorine is 4.0, carbon is 2.5, hydrogen is 2.1. So we assign these values: 2.1, 2.1, 2.5, 4.0, and then we make the dipoles. We analyze each bond separately. So from here to here there's a dipole, here to here there's a dipole, and these are going to be small because the difference is only 0.4, but between this and this, that's a difference of 1.5. So we're going to make the dipole bigger. So you should make the arrow consistent, agree with the difference in En between the two atoms. So you see that all these arrows are, this one's kind of like an oddball arrow, but these arrows are pointing this direction down like that. Okay, so if the arrows point more or less in the same direction, it's going to be polar. Sometimes you'll see the shape cause the arrows to cancel and it'll make it non-polar. Okay, so this molecule is polar. Okay, so we'll take a look at number 3, and then I'll post the answers to these. So number 3, your central atom, AS, it's in column 5A. Here's AS, column 5A. You see that the shape is going to take after this, the dot structure. So you have 3 single dots on the dot structure, and you're going to see that that's why you have this shape right here. So I don't know what just happened, but the shape looked like this, and it had the 2 single dots like that. So the 3 single dots that you see here give rise to these bonded atoms that are like that, and then the lone pair just kind of sits on top. And the lone pair, since it's negative, it's electrons, and these bonds right here are, there's 2 electrons here, 2 electrons here. All these electrons are so close together, and they don't want to be, so it ends up repelling the bonded atoms downward. Okay, so you get these bond angles like that. Okay, so instead of a shape that looks T-shaped like this, these electrons don't want to be so close to each other, so you end up with a pyramid shape in order for the atom to have stability. So this is going to be, the name of this shape is, let me try to see what happened with my shapes here. See if I can recover this. Well, I kind of lost my shape handout, but if you follow this on, anyway, if you follow the 5A, if you look, here's part of my shape handout, but if you look at 5A, you're going to see trigonal pyramid. You're going to see this shape right there, and the name of it's trigonal pyramid. So when you go to draw it, it's going to look like this. AS, CO, CO, and CO. Okay, these are 3.0 for En, fluorides, chlorine, and arsenic is, you're going to need your En table. I know offhand that it's less than 3.0. I'm just going to take a guess. It's around 1.8. I'm just guessing, but I know it's less. So now we add our dipole arrows here, here, and here. So you see that they all more or less go in the same direction, so it's going to be polar. Okay, so that concludes our tutorial. There's a couple things here where 4A, there's been a lot of questions about 4A. When is it polar? When is it nonpolar? You should have in your notes that 4A and 3A, so this shape and this shape, if you have the same atom attached, it's going to be nonpolar. So for example, this one is nonpolar, but if you have a different atom attached, 4A, 3A, it's going to be polar. So for example, you have two H's, two Brs, two bromides, or bromines. So these are not the same, so this is going to end up being polar. The dipoles, as you saw in the previous example, get a little complicated to analyze. So this rule of thumb, it works every time. Okay, so for 4A and 3A, so we'll look at a couple more. So like BH3, this is a 3A, so here's boron, it's in 3A. It's going to end up making this shape here. Same atom attached, it's going to end up being nonpolar. Okay, but if you change that up, if you have like two fluorines and one H, it's going to end up being polar, that one. Okay, so we could show some quick scratch work here. BH3 and BHF2 and BHF2. So BH3, the dipoles are going to wind up going like this. These two basically make an arrow like this. This is why I kind of came up with this rule. It's a little difficult to analyze these dipoles, and you need a little bit of vector background. So these are going to cancel. Meanwhile, if you have this one here, this fluorine is going to make a massive dipole arrow because it has a huge difference in En like that. And this one will make one, but not as great as these. So when these two arrows add up, it's going to produce a very big dipole arrow like that. This one will kind of cancel with it, but this one will overpower it, and this one's going to be polar. That one's nonpolar. The same thing will arise with 4A. Okay, so same atom on 4A, 3A, nonpolar, different, polar. Okay, and hopefully you find this useful to you. Check online. I'm going to have the answers for this and this, the complete answers. Try to work them out yourself before using this tutorial. Alright, hope it works for you.